Hello, everyone, and welcome to Live from the Lab. This is the show where we talk about different technology that Bruker's developed to help scientists discover the world around us. Today's topic is about single crystal diffraction, specifically using high-energy wavelengths like silver in order to collect the next level of data. What exactly does that mean, and how can we dive deeper with this noble element? Well, we're going to head on over to the table and talk with one of our experts. Good morning, Michael.
Good morning, John.
Thanks for joining us.
Thank you for having me.
So this is a very, very exciting topic, I guess, huh?
It is.
It's more exciting than copper.
It is. So silver is exciting because it opens this plethora of new applications, not maybe new applications, but it makes them so much better.
Why is it important? I mean, so I know we've got copper, we've got moly, right? And I understand there we got difference in wavelength. Moly's a little bit higher, copper a little bit lower. Changes the peak positions, things like that, spreads peaks out, more accuracy. But why silver? Why do we push it?
It starts with the energy, so it's higher energy, so shorter wavelength, 4.56. That's 22 kilo electron volts. What that means is we have really a couple of advantages.
Okay.
So we have a better D-spacing. So we get to a higher resolution in single crystal talk. We get a lot more reflections because our Ewald sphere is larger. Compared to copper, we collect 20 times more data. And that is really important for statistical leverage. We'll see that later. Absorption is minimized. Extinction is minimized. With lower absorption, we really don't have any air scatter. Or very minimized.
Yeah, that's great for capturing that low signal in the background.
So everything is just crisper. Our diffraction pattern is compressed. We have more reflections per frame. Our processing works better. Scaling works better. Data integration. It's just a leap forward in making data quality better.
All right. So, I mean, you kind of sold me on this. Silver.
I hope so.
It's a great thing. But the question then is, if it's so good, why now?
Why now? It's about intensity.
Okay.
And it's one of those rare moments, I think, where everything comes together, like the perfect storm. To keep with that analogy, silver was on the radar for a long time, but it was just very weak. The sources we had, they were orders of magnitude lower intensity of what we can achieve now, and that was really problematic. Now we have the wavelength, we have the tools, and the application, and they all really come together.
So if we focus a little bit more on that source and the technological aspects out there, traditionally we had these sealed tubes, which were kind of large line focuses, and we could use those in points. We had some nice optics to go with them, but nowadays we're using these microfocuses, right? And that's kind of the key to a lot of this, right?
That's really the key, especially the modern microfocus sources. The diamond microfocus sources where we have a diamond heat spreader, and then we.
So there's actually a reason that we call it diamond, not just some marketing term. It's
they're not just premium technology.
Okay, so you're saying there's a diamond layer that actually helps to dissipate that heat.
There's a diamond heat spreader, and we deposit the anode material on top of that. And that really helps then to dissipate the heat much faster. Diamond is the best material for thermal conductivity. Then there is another whole set of innovations that I will talk about later. And that really produces very stable, high intensity microfocus sources, very small, high flux density beams that are much, much brighter than rotating anodes ever were for silver.
All right, so we got that really great source, and then the video, we had also seen you have this very nice optic, custom made to really couple to it. But if we go to the other side of the sample, now we're talking about detector technology, right? Because there we've also had kind of a little bit of an issue with higher energy wavelengths.
So the advantage of modern CPAD detectors is that they use a scintillator, a high Z scintillator, and that's super sensitive for silver radiation, for high energy radiation. That's very different from silicon detectors, HPC detectors that just do not work for molybdenum or silver, because we know that silicon is not a good sensor for silver, more than half, almost like 70% of the X-rays will just pass through a silicon sensor.
Yeah, I mean, it's like you say, I mean, right tool, right job, right? And in this case, we've got a nicely monochromatized beam, and in that case, we want to use something more optimized for capturing as much of the signal as we can.
Yes.
Yep.
So we have high sensitivity, photon counting, no noise detectors.
Yeah.
They're large. So with these detectors now in silver, you can capture diffraction patterns to atomic resolution in one detector setting. It's pretty amazing.
Yeah, and you know the other great thing about both of these technologies is this isn't the first go around on either. I mean, the diamond, which is a refinement of our microfocus technology, we're already on the 2nd gen there.
Yes.
Photon detector, we're already on the 4th generation there, right? So we've already got a lot of expertise. These are really tuned in.
You never stand still.
That's right. Always keep innovating, right? And speaking of innovative, I think the other bit of innovation is not just going high tech, it's also putting it in the hands of the people. And that comes down to sample handling and the actual software and that user experience, right?
It's all about usability in the end. So nowadays, what you see there in the picture was the automated goniometer head. Everything is magnetically mounted.
Really? So you just kind of like pop it on. All
When you close the door,
Yep.
The AI auto-centering jumps into action. What you see here, that little blue circle, that is where the AI sees the crystal with a certain probability and then moves it into the center. This is structure now. I had already filled in the atom types. Click, start, and then it just collects a full sphere of data. You see very short exposure times. I think those are, the default is 0.5 seconds, even with like silver radiation, in this case an organic molecule, which might not be considered to be ideal for silver. I also chose a sample that has a unit cell that's not too small. So we have 20 angstrom unit cell edges. You see the spots are nicely resolved even at a short distance. And at the edge of the detector there, we get to like 0.7 angstroms. So we're just ripping through this. We probably have collected, most of our data already. It's indexing. It will start integrating data. And then typically now, within like 40, 50 seconds, we get a picture of a structure. It's not, publication quality data. So here we see bispirazinone.
So that was all kind of an automated thing.
It was an automated thing.
Wow. So really, I mean, whether you're a novice or an expert, you can really appreciate having that type of technology, right?
Yes, yes.
Now, I did notice, too, the picture quality on that detector. It's so nice. I mean, you really get the highlights, you get the really bright things, but you can also see the low background, which, like you said, silver, inherently low air scatter. And then the other thing that gets me is, like, how nice the image is in terms of there's no, like, artifacts. There's no extra, boundaries, pixel things, anything like that. You just get a really nice picture. Every photon is really counted.
Yep. So what we do is we do photon counting in software. So we have all these tools that are available in our pipelining, FPGA programming. It's super high-end programming. Everything looks crisp. I'm not sure how to describe this better, but it's the diffraction images. Even if you do powder experiments, it looks like you have a background corrected diffractogram. No, there is no background. It is this truly amazing. We love our silver instrument.
Yeah, and it's the speed, like you said, too. It's that now with that intensity, you can get that quality at such a fast speed. So.
It is fast, even for samples where you wouldn't expect to have the best benefits.
So now, I guess you've put together some more slides so we can dive a little deeper into this, look at some more specific examples, some results you can get with silver, right?
That's true.
All right.
Let's
take a look at
dive into
it. Slide in. You're hilarious.
So, again, what we see is that silver radiation is becoming increasingly favored even over molybdenum because of its advantages. The shorter wavelength has a lot of benefits.
So I've got a question for you then. So you're talking about silver and moly there. Now I know a really popular option too is like we got these dual source systems. Would you always do like one of those higher ones like moly and silver and then copper? Or is there a time you would do silver and moly?
There is a time where we do silver and moly,
Okay.
and we do have one in the app lab. And this is when we look at the heat map here on that slide. This sort of maps the application to the wavelength, the application to the instrument. And we have these cases and a instrument that we call the HE, the Adventure HE, where we combine moly and silver. This is really geared towards the people who do solid state chemistry, inorganics, intermetallics, high pressure work. So the work that is really geared towards harder radiation.
Yeah.
Moly still provides you with the advantage that you get higher flux density.
Okay.
So this is a good combination. So we like our heat map because it really shows you and maps your application to your to the instrumentation and wavelength. Where I list here the advantages of silver, moly, and copper. And you see when you look where silver performs best, so that's the really dark color, that almost completely replaces a molybdenum now.
Yeah.
There's only a couple of applications that benefit from the higher flux density. But then if you have a lab that requires the whole wide range of applications, that's where we place what we call the Adventure VX that combines silver and copper radiation.
Okay.
Because then you have the perfect match and the perfect versatility, V for versatility.
All right. And with silver too, again, we need to remember it's not just about that, getting a silver source, because there are, you can get silver sources different places. It's really this silver source is the one because of the heat dissipation, the better technology, but also then having that detector.
So the color coding of that heat map really includes the intensity of the source and the sensitivity of the detector. If you produce a lot of silver diffraction or diffraction from a silver source, but you cannot detect it, silver doesn't help you. So things have to come together. So here again, just 2 slides of the advantages of silver radiation. High resolution, that is really directly related to the shorter wavelength, the higher energy. We really have reduced extinction effects. That is very important for quantum chemistry, where people look at the charge.
Yeah, because even if you got a little sample, you still can see those effects if it's heavy scatterers, right?
Yes.
Yeah.
We just have a better penetration depth. You get better data. Of course, reduced absorption, we talked about that, and I will have examples for most of these, and really improved overall data quality. If you get a data set, if you compare moly and silver, you will always win out with silver. It was like hard to accept for me initially, but it really is true. So all these advantages play together very nicely to give you a much better data quality. And not to forget, because you have the compressed diffraction pattern, your efficiency for collecting data is also much, much better.
So then, we said silver and moly, and it compresses our reflections, right? So it puts them closer to each other. Does that mean that, we also could have a problem with peaks starting to overlap or spots overlapping? Or is it that our detector technology is so good now that that's not as big of an issue?
So what you had seen on with the example, what you had seen with the bisphorazolone, that's a 20 angstrom unit edge. cell edge. That was collected at 40 millimeters, so very close, and those were well, separated.
Yes. Yeah.
But you can imagine, if you move the detector back to 60 millimeters, you get 1.5 times the spacing compared to that. So it's no problem to collect data on 50 angstrom unit cell edges, even at what is considered to be a standard data collection distance of 50 or 60 millimeters.
And the nice thing, too, is when you move that detector back with silver, you don't have the losses due to the air scatter. So maintain that intensity.
You actually even get less air scatter because it falls off with R squared.
Yeah.
No, I mean, I haven't really run into problems with like only advantages. I see only advantages of the compressed reciprocal space.
Okay, great.
Here's an example, just to give you an idea, an example of how X-ray transmission works. Sometimes people forget that Lambert-Beer's law is exponential, where the absorption coefficient mu sits in the exponent, and that means that absorption is not linear. So what that implies is that if you have a smallish crystal of 35 by 55 by 65, this is a real example. For copper, in this case, it's almost 100 reciprocal millimeters. That drops down to silver at 33 reciprocal millimeters. But when you look at the transmission, it's not linear. So this gives you an idea why even when people say, oh, copper is fine, I have a strongly absorbing sample, I just use very small crystals. Yeah, that's only true to a certain extent. You see that the transmission through the 35 micrometer part of the crystal is only 3%, and it goes to below 1% for 65 micrometers.
Wow, really?
And that's because
so as it changes in the beam, the direction, it's changing that much.
Yeah, and that's because it's an exponential law.
Yeah.
And although the absorption coefficient only drops by a third, you see our transmission is tenfold, more than tenfold, even for the 65 micrometers. And this is why you should think really hard by saying, oh, I can use copper for everything.
Right.
So silver radiation is really most beneficial for quantum chemistry, formerly known as charge density. Periodistribution function.
The new fancy name.
Yeah, periodistribution function, where you get the higher Q. And then we see a lot of interest from the battery research community for in situ.
Oh, yeah. PDF. Yeah, I mean, you shoot through a cell. And
material chemistry, low absorption, low extinction, solid state intermetallics, and then high pressure work. One of my favorites, where you have the compressed diffraction pattern that helps you, the lower absorption and the higher resolution. Also, we deal with a lot of scatter there, and that is dramatically reduced because we have to shoot through diamonds. We have to shoot through like 2 millimeters of diamonds. Those themselves produce a lot of scatter.
Now, it's also helpful probably in that case because those diamond anvil cells, they kind of limit your geometry. So by compressing the reflections, gives you more reflections in your space.
Exactly. You have more reflections and also to higher resolution.
Wow.
So let's look at instrumentation. Again, we had seen some images. Here you see like a marketing quality image of a dual source system in the enclosure. We had already looked at the sources and the detector. This is, by the way, the new design for the Diamond 2s.
Okay.
A little sleeker, a little more angular. So what I will be talking about is the Diamond 2 silver X-ray source that really surpasses the intensity of traditional molybdenum moly microfocus sources and silver rotating anodes. And that's, I think, one of the driving factors why I would say now our silver copper dual source system is the most preferred solution.
That's one of the things I really appreciate too with these microfocuses is that you get the same intensity over time. I mean, so if you measure a sample one day, say you get your results, you submit a paper, and then all of a sudden you get, the editors are writing back to you, hey, could you do another measurement to check something? You can be confident when you walk up to that machine, that intensity is going to be nice and stable.
I would drive it, I would push that even further, that statement. To me, it's more like I can walk into the lab every day and I know this thing will be stable for the next 5-7 years, and I don't have to, make expensive purchases. That's even more important to me.
Yeah.
Rotating anodes need a lot of maintenance, and they decay pretty quickly because you basically put a groove into the anode. On the detector side, the most exciting thing is that we have up to 95% quantum efficiency or absorption efficiency for silver.
Even with silver?
Radiation. Yep. So especially for the HE applications, silver single source systems and moly silver dual source systems, we offer a special phosphor that has even higher absorption efficiency. So here, just a quick overview before we look at a more technical picture. The secrets to the new sources are the diamond hybrid anode, the higher brightness cathode, and an active electron optics. Very high intensity. They're air cooled, which is really important to me. They have long lifetimes, and we guarantee them for 3 years. So that is a big one. All our systems are air cooled. There's basically no placement requirements. We could roll one in here and run it. I think the biggest hurdle would be to push it through the hallway, but we would have this up and running probably within an hour. In the lab here.
That's something that I think sometimes people just find unbelievable. I mean, I remember once I went into a discussion with a customer about a microfocus system versus a conventional system, and they just couldn't believe ever that something, of the wattage and the air-cooled nature of these microfocus sources could compete with the more, conventional, almost incandescent tube-like or light bulb-like sources, right?
Yep.
But it's amazing when you get rid of the losses and you really are highly efficient in the photon capture with coupling that optic.
Yep.
And what you get out of them. So, the proof is in the pudding. If anybody out there is being a little on the edge about this, I mean, remember you can always send in samples. You can contact us and we can run something for you. And the proof is going to be in those results.
We love to collect data.
Yeah.
Ashley likes to collect data. So here's a schematic of the Diamond 2. So one of the...
Are you showing a little too much here, Michael? Are we sure we can show all that?
We can show all that. We have nothing to hide.
All right.
So one of the big changes we did was we replaced the traditional cathode with a dispenser cathode.
Okay.
Because we wanted to have more electrons.
Yes.
So the dispenser cathode gives us a much higher flux electron beam. And now the secret is that we have electron optics that you previously only found in the metal jet type sources. Now we can shape that beam, and we can focus it even more. Because after all, we have microfocus sources, so we want to have a very small electron beam. We want to have a very small electron beam because this is where heat dissipation works best. If the beam is very small, we're not limited by the diameter, by the circumference of where the heat dissipation works best. It's a two-dimensional problem. And now we have silver deposited on the diamond heat spreader. We get rid of that heat very efficiently. And then also for the Diamond 2s, we have these very, very exclusive optics. These are 25 centimeter optics. They're very long optics. They're basically synchrotron quality optics. They're pre-configured substrates.
Wow, 250 millimeters.
Yep.
So those, I mean, I'm used to these 50, 100 millimeter mirrors.
In single crystal, we get the good stuff.
Yeah. Well, I mean, that explains the photon capture then.
Yeah.
With that huge optic.
Yeah. So we have, high flux density on the electron beam. It gets shaped. We have best heat dissipation. We have the best optics. Everything is made in-house. We control everything. And this is how you make a great product. Nice also, I forgot to mention about the electron optics, is standby mode is now very easy. You defocus the beam.
Really? So you can actually have, it'll change the electric field?
So the beauty about this is that the X-ray source or the tube then always stays at the same temperature. So there's no degradation from heating it up, cooling it down by bringing it into, it gets defocused, and that's it. It also means if you have a dual source system, switching is now instantaneously. So defocus one, focus the other one. And you have switch your wavelength.
Oh, wow.
It takes seconds now.
And no heat up time, no waiting for things to equilibrate?
No. It's very, very fast. The Photon 4, it's large.
That's an important thing for detectors, right?
It is very...
Size does matter here.
It really matters. It matters because you want to capture all the diffraction pattern. And the more reflections you have on a frame, the better processing works. It's very modern technology. We do photon counting in software that gives us interpixel logic. We can, for example, capture photons that are spread over multiple pixels when they hit at the interface. Typically when you see marketing material, a photon always hits in the center of a reflection, in the center of a pixel.
Of a pixel. Oh yeah, that's how it is.
But it doesn't do that necessarily.
And it's fully absorbed right there in one point.
Sure.
Yeah.
But if it hits in an interface, what happens is that your signal gets spread out over multiple pixels. If you apply a simple threshold, you lose that because because if you split it up, you're below the threshold. That's how you lose photons in HPC detectors.
Even more so than just photons, you can lose a whole reflection if it just happens to be in the wrong spot, right?
Yeah, I mean, of course.
Yeah.
And really important in this case is the high absorption efficiency for moly and especially silver. And because we use a very thin scintillator, we also don't have any parallax. So here's a good representation. People don't realize how thick in the lower image, that's like the sensor, the silicon sensor of a HPC. It's very thick. Typical sensor are like 600 micrometers to like a millimeter.
Okay.
0.6 to a millimeter. And the scintillators are very thin. They're like 40 micrometers.
Oh, wow.
So you get the idea. If you have an X-ray photon coming in at an angle, and because the absorption efficiency is so low, the interaction with the silicon can happen at any time here. And that means if it happens here, I get my cloud and it goes into this pixel. If it happens here, it goes into this pixel. So your signal gets smeared out. As soon as you come in at an oblique angle, not like in marketing material, we're always hit like perpendicular. When you smear out your signal easily over like 10 pixels. And then a good point spread function doesn't exist anymore because you smear out your sample, and you can never recover that loss of information. That's just another form of noise. The nice thing, if you have a high Z scintillator, your signal, it doesn't matter at what angle you come in. It will be produced in the first few micrometers. And then your point spread function is very low because it always produces a signal, at the same
in that
pixel.
That same
or
spot.
pixels if you hit it between pixels. But then with interpixel logic, we are able to capture that signal anyway.
So it'll actually then like reassign it to the proper pixel? It'll say, hey, I've detected 2 photons, but they're kind of low on energy. It's over here.
It will not, it cannot really tell from which pixel it came, but it will, what you will see on the diffraction image is you have a signal that corresponds to less than a photon on multiple pixels.
All right.
Yep. So here are some examples that I thought were cool. This is an example for a strongly absorbing sample. And what I want you to look at is, R values. Maybe turn on the laser pointer. R values are much better. Residual densities are much better. Although we have much more intensity here. Data collection times are comparable, but overall you get the much better structure. PDF with the detectors now being photon counting, with having really strong X-ray sources. The geometry is right that we can collect data to very high resolution. PDF analysis is now very doable on single crystal instruments. We also don't need, the high resolution you traditionally thrive for in XRD experiments. So this is a good example where we can creep into the XRD domain where we have some advantage in collecting really good data. And as I said, there is a lot of interest from the battery folks. Unfortunately, there's nothing I'm allowed to present there.
Well, what's nice, it's nice, like you had said, is that you can start using the system for other things. Just because you decide to buy a silver system doesn't lock you into 1 or 2 applications. I mean, you had that whole list of applications that you can do. And then if you do even the dual system, bam, you throw that other radiation, you got even everything. And it's not just kind of like, okay, everything. It's amazing everything. Right?
It's amazing everything, It's really, it's a premium product.
Right,
just from application. People like to do powder and single crystal work.
Well, that looks fun.
Yeah, you recognize these? Call them Debye rings, or?
Well, I was going to say, I mean, and you can see that spottiness, which tells us about the texture of the powder or the particle size of the powder. But what's going on with those really big old bright spots on the left?
Those are the diamonds. Those are the diamond reflections from the anvils.
Oh, so this is a high pressure experiment.
Yep.
So you can get this quality through a diamond anvil cell.
Yes. And what you see here is a good example. We'll show you what people were after in this experiment. But what you can see is one of the image on the left, that was collected at 70 millimeters, and then the other one at 150. So what you also see is that, again, because amorphous scatter falls off with R squared, at 150, you not only get a better separation off the lines, but you dramatically cut down on the amorphous scatter.
So you're telling me that the right one is also while in the diamond anvil cell?
Yes. Yep.
Wow.
That is
because that background scatter, like you said.
Yep. So here, I mean, this is what I want to show you. This is, they were looking at the spatial resolution, and so the diffractogram almost looks like it's background corrected. So this is actually the diffractogram from the 70 millimeter data. And what we were interested in is, this double peak here. And then the question is, if you move the detector to 150, is the divergence good enough? Is the detector, the point spread function good enough? Can we resolve that? And of course it is, or I wouldn't show the slide. So here it's at 150.
Oh, wow.
So, you know, it's nicely resolved, customer's happy. And this is striking to me. We just did another analysis on a intermetallic where people were just struggling using traditional wavelength. And, you know, Ashley always gets excited anyway, but she was doing her little dance when she saw the factogram in the lab using silver. So, you know, we are really excited, and I'm repeating myself about the data quality and the capabilities you have with silver radiation.
At what point are you going to show me the example where you go, so we found the boundary where that silver is just not so good?
I tried to push it, and I have sort of a surprise application where I didn't think this would work. So no, we're pushing it very hard. More traditional single crystal high pressure work.
Uranium. Well, there's an absorber.
There's an absorber, and what people also like to do now is to have two samples in the high pressure cell. For single crystal, it's actually, again, really perfect almost, because our beam has just the right size to shoot through the aperture but hit both crystals. So we can treat that as a two-domain problem, which then also increases our completeness and also our multiplicity, because we just have more observation by looking at more samples at the same time. So software is also a big part why all of this comes together so nicely. So you see, this is a 3.69% R value. The completeness is like almost 100%. That's like almost, that's a perfect.
So now this sample, was this like a natural thing where the quartz was stuck on it, or you actually stuck it?
The quartz is in there for, it measures the pressure. So gold is used, quartz, ruby, very traditional, where you look at certain properties to determine the pressure. This is your pressure gauge. Should have mentioned that. So this is the refined structure. There were no restraints or constraints. It was just a really beautiful example. Diffuse scatter, that's just I collected previously, and it's very psychedelic. I have to show this. This is the diffraction.
Amazing.
That's the diffraction pattern. These are 20-second 0.5 degree frames. It's sped up, I think 64-fold. What people are looking at with these lead halide perovskites is sort of the dynamic, composition-dependent nanodomains. A lot of big words. And what they're interested is in basically how those govern the microscopic optoelectronic properties. That's what they're looking at. And that somehow, don't ask me, I read the paper a couple of times, that's revealed through diffuse scattering and other methods.
Well, I mean, what's really amazing, right, about perovskites is it's that versatility in the structure that you can have the unit cell, the fundamental constituents of the unit cell can stay the same, but just by moving around the internal bits just a little bit, we get amazing properties.
Yeah. You have this tilt of like the octahedra.
Yeah, you just have it move a little bit, and all of a sudden, because of that change, we get these awesome properties which couple electrical and magnetic fields and things like that. But man, that is tough to do with conventional diffraction techniques.
So here, in this case, what they're interested in is to look at these very weak signals next to very strong signals. Here, if you can appreciate the little square here, it's a rectangle, and then this is the 3D view of it. You also can see, the black, that's where the beam stop hole in the beam stop is, and then you have, these very, very weak diffuse scatter. These scales are a little deceiving, but we have to use them to show reflections that are really, orders of magnitude stronger. Wow. And what you see here, the diffuse scatter, this is just down here in the background. It's almost impossible to show both at the same time.
Yeah, it's kind of like this HDR signal that you need. Right?
Yeah. But that is like super HDR.
Yeah.
Then Also, if you look at organic molecules, you could argue, oh, it's fine to get a picture and it's like 0.83 with copper. Well, why do I need higher resolution? And you just get more detail. So here's an example of tautomerism and keto-enol tautomerism. And there's like, just like, let's turn this on again, just like here, where you have or here, where you have very well defined a hydrogen that's hydrogen bonded between these two oxygens. In this case, it's actually disordered. And only when you go to a higher resolution of a better despacing of 0.6 angstroms, you can see that. At 0.8, it's just a blob.
Yeah.
So this is where detail matters, and it matters, for example, for the pharmaceutical industry, where these effects can really change the solubility, bioavailability of drugs. So you need to know about them. Yeah. This is a good reason why you should not just settle for the second best. Try to get the best data you can collect. Absolute configuration. If you would have told me, like, probably half a year ago, go and do absolute configuration with silver, I would have told you, no, go away, that's not possible.
Not going to happen.
Yeah. So here's an example, and I'm not advocating you should get a silver system to collect absolute configuration, but this showcases how good our instrumentation is. That is a clearly determined absolute configuration for a sucrose, which I thought would not be possible. The flag parameter is very decent. This is data to 0.35, very respectable R value. We actually were using these data sets to look at charge density, and then we didn't actually go out and try to do absolute configuration. This is sort of a side effect of good data we collected. And it's very interesting. We thought hard about that, and there's a researcher in Spain, Jordi Bennett-Buchholz, who has done a lot of work on moly. And basically what it comes down to, and I mentioned this before, is the 20-fold increase of unique data for silver compared to copper. This is what it makes it possible. The interesting thing with the resonant scatter, the anomalous signal, is that it stays pretty much constant over the whole range in 2 theta. And that is very important. So when we look at our anom, that sort of explains why this is possible. So it measures the Friedel differences in a normalized way, where it compares the absolute intensity difference between a reflection and its Friedel mate to their average intensity. Basically, resonance scattering is typically when you have a plane, it doesn't matter whether it gets diffracted from this side or this side, but if you have a non-symmetric structure for certain reflections, this is not true anymore. Right. And that minute difference in intensities is used to determine the absolute configuration. So our anom is often misinterpreted as a direct measure of the anomalous signal, but it's really primarily a statistical tool. So what I want to say is that absolute structure determination does not depend on having a large R anom or a large difference in these Friedel pairs, although that helps. What truly matters is that the Friedel asymmetry is consistent over that long range. Right. And because we have 20 times more data, we can use that for a statistical leverage. And then even when the resonant signal is very low, if we have good statistics, good accurate data, good good sigmas of the data, we are able to do that. So this is basically why it works. And again, with the silver diamond 2 and the photon 4, the system achieves unambiguous absolute configuration of sucrose. And so the long considered impossible task, becomes a definite demonstration of the instrument performance. So for me, this is just like the proof of the pudding. The data I'm getting from these type of instrumentation now is so good that you can achieve something that was considered to be impossible. And that is, I think, what really matters. A short summary, we're running short on time anyway. And that gets back to the perfect storm. When the wavelength, the source brightness, and the detector efficiency are combined, the systems enable structural insights that are difficult or inaccessible with conventional moly or copper setups. I think this is the message. We're opening a new avenue for people to be able to collect better data, add new capabilities to their labs, improve capabilities that they already have. And as you mentioned before, if you combine silver with copper, you have the perfect system. You can do protein work on one hand, and you can do intermetallics and quantum chemistry on the other. You cover all your bases.
Yeah, and with the technology, what it sounds like to me also is that we're not just saying that we're, setting a new high. It's not just that we're saying that in the lab we can do these things never done before, which we certainly are. We're also saying that we're really setting the bar, not just the high, but we're saying this is what everybody should have.
Yeah.
Right? We're making it accessible to everybody. This isn't just the Ferrari that only a few people can have. No, this is a system that everybody should have, really.
It's now, I think, if you talk about a Ferrari, it's a road legal Ferrari.
Yeah.
I think that this is what we're putting into into the driver's hands.
Yeah.
A road legal Ferrari. I like that. Yes.
Yeah.
I mean, we're a German company. It should be, of course, a Mercedes. Or,
Mercedes. This is bringing the Maybach features into the everyday driver. Huh?
Yeah.
Okay. So thanks for that. Now we do have some questions that did come in before. By the way, if you ever see a live from the lab topic you're interested in, you can send those questions in. If you're watching this later, you can send your questions in live.events@bruker.com. We'll get back to you. If you're watching right now, go ahead, type those questions in. We'll chat about those things live. But start out with, Philip was asking, what has changed that silver sources have become so strong? And I know that you kind of had gone over that, but what were those key points? Why now?
Key points, new dispenser cathode produces more electrons that are, focused with electron optics onto the anode. That has better heat dissipation, and it's coupled to a very exclusive, a very well-working optic. All these combined produce intensities now that are 3 orders of magnitude higher than what I used first, a normal fine focus sealed tube, silver sealed tube.
Yeah. And that's that other point too. These are very high performance. We're talking about going up against rotating anodes. If we go back to that car analogy, it's like we're getting the race car performance, but not all the maintenance. We're not having to replace the engine at every race here, right? I mean, this thing just works and works day in and day out. Man, and anytime you get rid of water cooling in a lab, I am all for that. I always hated water. It's always been a problem.
Water's problematic.
Yeah. All right. Marion was asking, why are sensors for photon detectors so thin and silicon sensors are so thick? So you said why that's bad to have a thick sensor. But why is it that the photon can have a thin one while the silicon has to be thick?
So the scintillator is a high Z, so typically gadolinium sensor. And because it absorbs the X-rays so well, and then you have, the interaction that produces the signal in the first few micrometers, you don't have to make them very thick.
Okay.
If you have a silicon sensor, to make it work at all with molybdenum or silver, you have to make them very thick to have any interaction at all. But that, of course, comes at the expense of other problems like parallax.
Yeah, I mean, we've talked about how we love the silver radiation because of its lack of absorption in the sample, because it can shoot through there. But then, that kind of hurts you if you're using the low Z detector. So, Francis, should we now do all absolute structure determination using hard wavelength?
No.
Is that what you were saying here? Is that only every absolute is done here in the lab with silver?
If you want to impress your significant other and show that you can do absolute configuration using silver, that's fine.
Yeah.
But please don't go and run to your faculty and say, I need a silver source now because I want to do absolute configuration. I think that's the wrong message. The message is really, hey, look what we have seen. This is fantastic, and it's only possible because the system performs so well. Mm-hmm. The noise is so low. The data is so accurate. The statistics are so good that we can really appreciate now these very small signals being determined so perfectly.
Awesome. All right, Juan asked, what is the divergence of copper, moly, and silver microfocus sources?
Let's start with copper.
Mm-hmm.
We're really looking, especially for small molecules, we're looking at the highest possible flux density. Mm-hmm. And there's a direct correlation between a divergence and intensity. So those sources are typically, from the optics, have pretty high divergence, 13.9 millirads for the copper. I think the diamond, let's call it 14. But that allows you to use collimators to stop that down to lower divergence. But the law states that if you halve the divergence, the loss of intensity is squared. So if you halve it, you only get a quarter of the intensity. The good news with moly and with silver is that the divergence there is like below or just around 5 milliradians. That means you natively get like a really, really low divergence. In I have never really stopped down moly or silver because the divergence is very low, and I'm certainly not pushing to collect protein data using hard radiation. Although, if you have a lysozyme, you're perfectly fine to collect that on moly. Silver and moly pretty low at around 5. Copper, from the mirror, pretty high, but you can stop this down with collimators that are kinematically mounted. So exchanging those just takes like 2 seconds.
Yeah.
Very easy.
All right. And then last question we had that came in before is from Louise. What is the maximum resolution that you can reach with silver?
2D sine theta equals n times lambda. So we have 0.56. Divide that by 2. That is sort of 180 degrees. That would be the physically the max. But then, of course, you have bezels on detectors.
Yeah.
I have collected data sets to 0.284 angstroms. Oh, wow. So that is pretty amazing. Yeah. So that's the highest I have achieved using silver radiation.
Wow. Well, I mean, that's amazing when you talk about that type of a resolution from a system that's like a macroscopic measurement, right?
Yep.
So, and it works in air and without water cooling.
Yeah, you like that.
Oh, I love that. I tell you, that is like, yes, that is the best thing, especially for a regular lab, right?
Yeah, it is.
I mean, this isn't like the beamline facility where they have all these technicians working. No, we just want a system that works. Like you said, you walk in on a Monday and you know this thing's going to be working.
Yep.
Right.
Very
all day
important.
long. All right. So let me just check here if we had any other questions come in. I don't see that. Actually, here we go. From Gustavo. Can a silver microfocus source be installed in a D8 Quest Eco?
No.
Okay.
No, it cannot.
Which systems could it be installed in?
Everything but the very entry-level system.
Okay. So you could get not an Eco Quest, but a regular Quest?
Yeah, I'm now. Yeah, because the Quest Ecos, they have sealed tubes.
Okay.
Fine focus sealed tubes.
All right.
Moly or copper.
So you could go regular Quest or the Ventures and then up into the dual source.
So you certainly can get a single source Quest, and then the IMUS3 still exists. You know, that has still decent intensity. It's not, you know, the outstanding intensity of a diamond, but you know, if you go to lower cost solutions, the Quest with the silver IMUS3 and then a photon 4.8 detector, that would be your most cost-effective solution for, if you really, and what I would tell you, you should get for a silver system.
Yeah, you know, and if you got a question like this too, feel free to reach out, and we can help you, you know, figure out a good path.
Yep.
You know, if you're in an eco now because you got started in the whole single crystal realm, and now you want to enable your lab in the next level, we can also help you with, you know, take some data. Maybe you can show it to lab management or write a grant and get that next level.
We're always happy to collect data.
Yeah. All right, next one from, let's see here, Tangan Subaskar. Sorry if I did not say that right. 2643. Can silver radiation measure trace elements in cement to ppb or ppm levels?
That's really a different application, I think.
Yeah.
So, you know, this is more like X-ray fluorescence. So we do not really measure trace elements because if you have a trace element, an example would be a ruby, you know, where you have just trace elements of chromium, which gives it the red color, you will never see, in a single crystal experiment, you will not see the chromium.
Right, yeah. Yeah, or things like doping in silicon.
Yep.
It's that those dopants are so far apart that, you know,
So, I mean, if it gets to like, if it gets to a level, you know, where we really introduce defects, maybe going back to what we had seen with the diffuse scatter, where the defects really induce diffuse scatter, then you would be able to model macroscopic, you know.
Right, right. Yeah, and actually that brings up a good point. Anybody who's watching, if you ever have questions just about these techniques in general, like single crystal diffraction, that's what we're talking about today, or X-ray fluorescence, or powder X-ray diffraction, we have a bunch of videos on our YouTube channel. It's called the What Is series, so What Is SCD? Also, you can always look back through these live from the labs. I mean, over the years, we've done quite a few of these.
Yeah.
And if you want just like primers on what the techniques are, those are good places to look. Sounds like, though, for you, for the cement, yeah, probably XRF would be the good place to look. Again, reach out to us. I mean, we've got XRF experts here, too, who can help you out with that.
That's a good one.
Yeah, we could. There's a few down the hall. All right, so that's all the questions that we've had. Michael, thanks for joining us this morning.
Thanks. It's always fun to be here.
No, this is great. I learned a lot about silver. I mean, definitely it seems to me that if I was to go out and buy one of these systems today, you got to get the silver one, right? Yes. I mean, if you don't, you're already behind.
You're behind.
You're already behind the curve. So
you're missing out on all the fun. That's the most important thing.
That's right.
Yep.
So, and thanks everybody out there for joining, spending your time with us. Until next time, keep your signal high and your background low.
Happy refining.